So for us to be in the same page, this is a classical system representation. We have a system and we have an input and we have an output. So the system G will be a function of the input. So we can write in a mathematical form that y is the output, is the G of the input. So the input is a signal that will operate in the system to produce the output. Yes. So the system G can be can be represented in several ways, and you could have, for instance, only a multiplication by a factor that would be a static system that doesn't change the dynamics of the input, just the amplitude, or you could have a complex set of differential equations here changing the signal input U to build the output Y. So this would be a dynamic system and not only a static one. So how do we get the transfer function? First, you need to have a mathematical representation of the system. Usually what we have is a linear ordinary differential equation as in one. So we have a differential equation relating the output y, the derivatives of the output y, with also the derivatives of the input u. Okay, a and b in this case are only the coefficients of these derivatives, and this here, for instance, is representing the derivative of order n. So when you apply the Laplace transform in this ODE1, you have the associated transfer function. So the transfer function is related is relating the output y with the input u by this rational transfer function. So we have, instead of the derivatives of order n, we have s to the power n. So this is the idea of the Laplace transform. So you don't have derivatives anymore, but you have polynomials. Okay? And here, the derivative of order m, you have the polynomial s of order m. So this numerator is associated with the derivatives of the control input u, and the denominator is associated with the derivatives of the output y. So g of s is equal y divided by u. Okay, we're going to see this in the next few slides. So in this notation, the k power of s corresponds to the k order derivative. So g of s can also be represented as n of s divided by d of s. That's just the numerator divided by the denominator. You find this representation in books, papers, and also as the output divided by the input. So s here is from the Laplace transform. The polynomial representation of the ordinary differential equation is given by, so we have ds times y of s, so is this crossed product here, is equal n of s times u of s. So we can have this relationship, and then we know that the numerator here is associated with the inputs and the denominator is associated with the outputs. So this equation also is a compact form of the ODE that relates the input u to the output y. So that's another way to write this. So if we have a linear time invariant single input, single output system, it can be modeled by a transfer function as given here, g of s. And if we have, in the case of multiple inputs, multiple outputs, we don't have a single transfer function, but we have multiple transfer functions. Okay, so you would have a matrix transfer function relating all the inputs with all the outputs. But the idea is follows the same pattern. Okay. So let's go for some definitions that are going to be useful in this lecture. First, a number S belonging to the complex number is a pole of the system G if, when I replace S in the denominator, I found 0. So for a number to be a pole of the system, it needs to be a root of the denominator. Okay, so all the roots of the denominator will be called the poles of the system. And this equation has a particular name. It's also known as a characteristic equation of the system G. So it's only the denominator of the transfer function is also the characteristic equation that you can use to find the poles of the system. And in the same way, a number S belong to the complex numbers as well is a 0 of the system if it's a root of the numerator of the transfer function. Okay, so if you have the numerator of the transfer function, a root of the numerator will be a 0 of the system. And the last definition here is of the DC gain, or also state-state gain, is given by B0 divided by A0. So the DC gain is obtained when you replace S equal to 0 in the transfer function. Okay, so G of 0, so everyone here is going to be 0. You have B0 in the numerator. All these coefficients times 0 will be 0, and then you have A0. So this is the DC gain, is B0 divided by A0. Poles, zeros, and the DC gain will be used to characterize the response of a linear time invariant system. This is also important to remember that there are systems that are not time invariant. Okay, so these techniques would not apply for time invariant systems, nonlinear systems. So here we are in the simple world of linear systems, time invariant. Okay, so if for other types of systems, you would use other tools. So these elements can be computed in MATLAB or Octave. Octave is also a free tool. You can use it online or you can download it using the commands pole, 0, and DC gain. For instance, we have an example here of an LTI system modeled by the following ODE. So you have an ordinary differential equation relating the output of the system and the input of the system. And what the first step would be to find the transfer function. So you need to apply the Laplace transform, and then you have the transfer function. Basically, is this what has been done here. So the transfer function you have in the numerator 3042 S plus 1014 divided by S squared plus 10S plus, yes, 169. So this is the syntax for MATLAB. So you can use the transfer function, and then you put the numerator. So this is the vector containing the coefficients of the numerator, comma here, and then the coefficients of the denominator. So 1, 10, 169. If, for instance, if you didn't have the y dot here, so you should put 0, okay? You cannot forget this because otherwise you have a different transfer function. So the commands are as follows. So if you include 0 of g, it's going to give you the roots of the numerator. if you use pole of g, it will give you the roots of the denominator, that's this equation. And if you use the cgain command, it will give you this value that's basically g of 0, just replacing 0 in the transfer function. So I made a script here that's basically the same that's in the slide, but later I will share this with you. So this is on MATLAB, so you can also use this clear to clear all the variables. CLC will clear the command window here. So this is one way to define the transfer function, okay? And all the commands that we have used up to now, so up to here. Let's check. So you can also write the function here, so you know that's okay, this is not this function. It's because I run everything and I just want this section. Okay, so g, okay, now is the right function. So this is the function, g is the 0. So if I replace this number in s, I will have 0 in the numerator, okay? And if I replace the poles in the denominator, I will also need to find 0, okay? So it's basically also, you have this command that's called roots. So if I find the roots of the numerator, for instance, it needs to be exactly the value of the 0, and it's true, so it's the roots of this polynomial, and also the roots of the polynomial in the denominator should be exactly the poles of the system, okay? So it's exactly the same. Systems that do not have common poles and zeros are called minimal systems. And for a minimal system, S is a 0 of the transfer function if and only if g of S is equal 0. Why this is the case? Because when you replace the value of the 0 in the numerator will be 0. So you have 0 divided by something, then it's a 0, okay? So that's why for a minimal system, if S is a 0 of the transfer function, you also will find that g of S is equal 0. And for the pole of a transfer function, if I replace S as the pole of the transfer function, I have infinity, because I'm divided by 0. Okay, so when you divide something by 0, you have positive or negative infinity, but here I'm taking the absolute value, that's why it's always positive. A system that has poles and zeros at the same location is called non-minimal system. Okay, and then you can find a minimal representation for a non-minimal system, and then we will see this in a minute. In this case, the transfer function is not well defined at the common point where both a pole and a zero exist. So you have a pole and a zero in the same place. For instance, here, consider the transfer function to s plus 1 in the numerator and s plus 1 in the denominator. So we have a 0 and minus 1, and also we have a pole and minus 1. So this is a non-minimal system. And to find a minimal system, we need to cancel all the common poles and zeros. Otherwise, the function will be not well defined in minus 1, okay? Because you have a division of 0 by 0. Okay, this is also sometimes dangerous when you design a controller to cancel a pole that's an unstable pole. So you could design a controller that would cancel the unstable pole. But in real life, what happens is the cancellation cannot be perfect, and then you still have something that will give you undesired dynamics in the closed loop system. So we need to be careful every time we have cancellation of poles and zeros. So to obtain the minimal representation, we cancel S plus 1 with S plus 1, and we have only a static system in this case. That's the minimal representation for the G transfer function. So in MATLAB or Scilab or Octave, you can use this function min_real to obtain a minimal representation of the system. We will only cancel the poles and the zeros. Okay, so just gonna show you. This is exactly this section here. So this is another way to define a transfer function. You can define S as a transfer function of S. You're defining the Laplace variable here, and then I just write G in the same form it was in the slide. So it's 2 times S plus 1 divided by S plus 1. And then I use the command min_real to get the minimal representation of the function. I will run just this section, and then I'll have G, that's the function we had before, and then G min, that's just a static again. In this case, they just cancel S plus 1 with S plus 1. Properties of transfer function. First, we can call a transfer function proper if the degree of the numerator is less or equal the degree of the denominator. We can call a transfer function strictly proper if the degree of the numerator is smaller than the degree of the denominator. We always want proper or strictly proper functions because they imply causal systems that can be constructed. Can be like you can have a realization of this type of systems. If you have a system when the degree of the numerator is greater than the degree of the denominator, it's a non-causal system. You could not implement this type of system. Okay, so we always are looking for degree of the denominator greater or equal the degree of the numerator. And a transfer function is stable if its zero input response converts to 0 as t tends to infinity. In continuous time, that's the case we are looking here today, the transfer function will be stable if all the poles are in the open left half plane. It means that the real part of the poles must be negative for a system to be stable. Okay, so that's why this open left half plane, you do not count the imaginary axis. So the real part must be negative in order to give you a stable system. Another property of the transfer function is minimum phase systems. If all poles and zeros are in the left half plane, so you have a minimum phase system. If you have poles with real part negative, but if you have zeros with positive real part, you have a non-minimal system. It's not unstable, but we will be seeing here what's the behavior of this kind of system. Okay. So given this transfer function that we have been working with, the first case is if you have m less than n, is smaller than n, you have a strictly proper, it's always causal, so it's it's okay, it's the case we want. If m is equal n, it's also okay. It's causal with possible direct feed-through. It means that the control input can have a direct effect in the output of the system. So this is this direct feed-through. So your input is actuated in the output of the system. Okay, they have like a link from the input direct going to the output of the system. So in this example here we have the case 1, right? Because this polynomial has a degree 1 and this polynomial in the denominator has degree 2. So it's a strictly proper system. To verify if it's a non-minimal system or non-minimal phase system or minimal phase system, we need to find where the zero is located. So it's the zeros and also the poles of the system. So I don't know if we have, okay, I have it here. So we can check. So this is the system, the numerator is 2 and 3. Okay, and the denominator is 1, 4, 5. So it's another way, just write the numerator 2 and 3, so it's 2s plus 3. The denominator is s squared plus 4s plus 5. So the transfer function of the numerator and denominator, and this PZ map function will give you a map with the poles and the zeros of the system, showing the location of the poles and the zeros of the system. It will give a figure, okay? Also, I'm here using this command isStable that will also be in the slides to check if the function transfer function is stable or not. And I'm also plotting the step response for the system. So let's see what's happening here. Okay, so let me go back here. So this is the pole zero map for this transfer function. So we see that the poles have a negative real part. Okay, so everyone is in the left half plane because 0 is here, so all the poles have negative real part, so this is a stable system. The 0 also has negative real part. It's also on the left half plane, so it's also non-minimal phase system. Okay, and then when I plot the step response for this transfer function, I have this response here. Okay, indicating that it's a stable system. So this is the characterization we are minimal phase. So it's a minimal phase system. Okay, so this is just the solution we have seen. The poles are in this position, -2 plus or less the imaginary number here, j. So this implies that we have a stable system. The zeros, in this case, we have only one zero, and it's located in -1.5. So we have a minimum phase system. So the conclusion of this transfer function is strictly proper because the degree of the numerator is smaller than the degree of the denominator. It's stable because all the poles are located on the open left half of the plane. Okay, and it's minimal phase because both the poles and the zeros are in the open left half plane, so they all have negative real part. Okay, if it's not the case, it's going to be called non-minimal phase system. Okay. So this internal stability is a property of the zero input response as t tends to infinity, and the LTI system is internally stable if the response to the input returns to zero as t goes to infinity for any initial condition. The system will be called internally unstable if it's not stable, okay? But then it's the zero input response is given by y of t. That's this sum of coefficients multiplied by exponential of lambda it, where each of these lambdas is a pole of the system. So it's easy to see that if lambda is a positive value, if the real part is positive, the exponential will just grow, okay? And if lambda is a negative real part, the exponential with time will decrease. Okay, so that's why the poles with a negative real part imply stability, because this is the answer of the system. Where this comes from? When you take the inverse Laplace transform of the transfer function, you have a function of the time, okay? And then you have these exponentials appearing because of the inverse Laplace transform. So if real part is smaller than zero, exponential decays and approaches zero over time. If real part is greater than zero, the exponential grows indefinitely over time. And if the real part is equal to zero, the exponential has constant amplitude over time, because exponential of zero will be 1. Okay, exponential of 0 will be 1, so you have this constant value here. The only issue we will be talk about is if you have repeated poles with real part 0, then the system will be unstable, because in the inverse Laplace transform you have a t appearing when you have repeated values. So a linear system is stable if and only if all poles are in the left half plane. That is, all poles have strictly negative real part for all I. So all the poles must have negative real part. So we have another example here. So there's a transfer function, denominator -2 and 3, so -2s plus 3, and the denominator 4s squared plus 7s plus 8. If I calculate the pole, I have here a real part negative, so it means that the system is stable. And you can also check by using this function is stable g1, and it gives you a logical 1. It means that the system is stable. Okay, I'm gonna go back here. So let's check this system, right? -2, 3, 4, 7, 8. So -2, 3, 4, 7, 8 around this section. Okay, this is the PZ map function. So the poles are in the left half plane, because the real part is less than 0, but the 0 is not on the left half plane. It's the right part of the plane, because it's a positive value. So the system is stable or is unstable? The system is stable because the real parts of the poles that are represented here by the cross here is they are negative. But this is a non-minimal phase system, because the 0 has a positive real part. And the effect of this non-minimal phase system appears when you get the step response of the system. In the step response of the non-minimal phase systems, before growing, the response goes below 0 here, okay? So you assume some negative values and then you go up. So this is the main characteristic of the non-minimal phase systems.